mid-February 1943 near Sidi Bouzid, central Tunisia. In the aftermath of the fighting around Sidi Bouzid, a lone American M4 Sherman came to rest in the open desert. Its engine was silent, its tracks half buried in sand, yet the white US star on its hull was still faintly visible beneath the crudely applied black German cross. Unlike most disabled vehicles scattered across North Africa, this tank had not been destroyed, it had been taken whole. Officers from Heavy Panzer Battalion 501 quickly surrounded the machine. Clipboards and notebooks appeared almost immediately. This was no ordinary battlefield trophy. The German army had captured an American medium tank in running condition, an event rare enough to draw the attention of engineers far beyond the front lines. What followed would quietly unsettle long-held assumptions inside Germany's armored development community. The lessons extracted from this single vehicle would not concern gun caliber or armor thickness, but something the German armored doctrine had consistently undervalued: a mechanical reliability on an industrial scale. Painted on the hull was the name War Daddy 2. Factory records identified it as serial number USA 3,067,641, manufactured by Lima Locomotive Works. It had served with Company G, 1st Armored Regiment, 1st Armored Division. Now, under new operators, it was about to begin an unintended journey that would speak louder than any intelligence report. A German reconnaissance detachment drove the captured Sherman approximately 350 kilometers across harsh North African terrain to the port of Sfax. The journey took 4.5 days. For German tank crews accustomed to frequent breakdowns even during short redeployments, the experience was deeply unsettling. The engine ran without overheating. The gearbox showed no signs of distress. Final drives performed consistently, mile after mile. Dust, heat, and uneven ground failed to provoke the mechanical failures German crews had come to expect from their own vehicles. Observers noted with growing concern that the American tank required neither constant adjustment nor roadside repair. By the time the Sherman reached the coast, its message was already clear: this machine had been built with a different philosophy. At Sfax, the tank was carefully loaded aboard a cargo vessel bound for Europe. Orders from the Heereswaffenamt, Army Weapons Office, were explicit and uncompromising. The vehicle was to arrive in Germany fully intact and in working condition. No shortcuts, no experimental modifications. German intelligence had long received fragmented data on American armored production estimates, tables, factory output figures. But standing beside the actual vehicle made those abstract numbers tangible. The Sherman embodied an industrial capacity Germany could not replicate: standardized design, automotive manufacturing principles, and production volumes measured in the tens of thousands. As the ship crossed the Mediterranean, German testing authorities prepared a detailed evaluation program. The results, they suspected, might confirm truths they had preferred not to confront. Spring 1943, Kummersdorf Proving Ground, Brandenburg, Germany. The Sherman emerged from its rail transport at Kummersdorf, the Wehrmacht's primary evaluation site for both domestic and captured armored vehicles, located roughly 25 kilometers south of Berlin. It now carried a German designation Zugkraftfahrzeug 259 and a Wehrmacht license plate, WH 58941. Engineers had already covered the tank's exterior with stenciled markings. Armor thicknesses, slope angles, and reference points were labeled across the hull and turret. This was not a superficial inspection. It was the beginning of one of the most thorough mechanical examinations German engineers had ever conducted on an enemy vehicle. Kummersdorf was where German armor concepts were tested, refined, or discarded. Every component, tracks, suspension elements, gear ratios, cooling systems, was subject to precise measurement and exhaustive documentation. The Sherman would be analyzed with the same rigor as any German prototype. Teams from multiple technical disciplines participated in the initial inspection. Photographers documented each assembly from dozens of angles. Specialists measured tolerances and clearances with fine instruments. Welding methods, casting techniques, and component layouts were carefully recorded. Many of these construction choices appeared almost disarmingly simple when compared to the complexity typical of German armored vehicles. it was the transmission that drew immediate and intense interest. German tanks relied heavily on straight-cut gears, components that demanded extremely tight tolerances and frequent servicing. These systems offered theoretical efficiency but proved fragile under prolonged field use. The Sherman, by contrast, employed herringbone cut gears, a design that spread mechanical loads across multiple gear teeth at once. This approach dramatically reduced wear and shock stress. In the United States, such gearing had been standard practice in civilian automotive production since before the war. German engineers had previously dismissed the design as impractical for large-scale military use, citing difficulties in machining and workforce limitations. Now they were forced to confront an uncomfortable reality. The Americans were producing these components not in dozens but by the thousands. Testing moved from inspection to operation. Controlled trials were conducted to push each mechanical system to its limits. The objective was not to find weaknesses, but to understand why so few appeared. What emerged from Kummersdorf was not merely an evaluation of a captured tank. It was a reckoning with a different industrial mindset, one that valued durability, ease of manufacture, and operational endurance over mechanical elegance. By the time testing concluded, German engineers understood that armored warfare was no longer defined solely by armor penetration charts or gun calibers. It was increasingly governed by logistics, production efficiency, and machines that simply kept running. And in that quiet, relentless reliability, the Sherman had revealed a strategic advantage Germany could neither ignore nor quickly replicate. American engineers subjected the captured Sherman tank, known as War Daddy, to an exhaustive series of trials intended to mirror the harsh realities of combat. The vehicle was driven repeatedly through demanding obstacle courses that simulated battlefield terrain, while specialists closely tracked fuel usage, engine heat levels, and transmission response under different loads and surface conditions. Once each test cycle ended, major mechanical systems were taken apart piece by piece. Engineers studied wear marks, stress fractures, lubrication performance, and any indication of structural weakness that prolonged combat use might reveal. What they found challenged long-standing assumptions within German armored doctrine. For years, German designers believed that high battlefield performance inevitably came at the expense of mechanical durability. The Sherman quietly disproved that belief. Across all measured categories, the tank performed competently, and in one crucial area, it clearly surpassed its German counterparts. Sustained operational reliability with minimal maintenance. The inspection of the Sherman's drivetrain highlighted a stark contrast in engineering philosophy. Its transmission offered 5 forward gears and a single reverse, with synchronized gearing from 2nd through 5th. This eliminated the need for double clutching during standard operation, making gear changes smooth and forgiving. As a result, driving the Sherman required little more skill than operating a civilian truck or automobile. Training time for drivers was short, and errors were unlikely to cause mechanical damage. German tanks followed a very different logic. Their crews were expected to master intricate double-clutch techniques and carefully manage throttle input to prevent transmission failures. This demanded extensive training and constant attention in combat, conditions that were not always realistic on a chaotic battlefield. At its core, the Sherman was designed around the assumption that ordinary soldiers, armed with basic mechanical knowledge, would be responsible for operating and maintaining it. German designs, by contrast, relied on the availability of highly trained technical specialists. The particular Sherman under evaluation was powered by the Continental RO 975 radial engine, which impressed engineers with its adaptability. The engine delivered stable output across a wide range of temperatures, conditions that often caused German engines to overheat, lose efficiency, or fail outright. Its cooling system, though relatively straightforward, proved remarkably effective. Equally important was the air filtration setup, which handled fine desert sand far better than German systems that frequently clogged during operations in North Africa. Every subsystem reflected a consistent design priority: real-world functionality taking precedence over theoretical perfection. This contrast became impossible to ignore during a high-profile demonstration held on June 6 and 7, 1943, at the Hillis Lean Artillery Testing Ground. Reich Minister for Armaments Albert Speer attended personally, joined by senior Wehrmacht officers and leaders from Germany's arms manufacturing sector. The event was designed to compare German armored vehicles against captured Allied tanks under controlled but demanding conditions. Among the vehicles assembled were the Sherman War Daddy II, a newly produced Panther OS-FE, and the massive Ferdinand tank destroyer widely regarded as the pinnacle of German armored technology. Speer, who answered directly to Hitler for production results, was keenly interested in what American industry was capable of delivering and how German designs measured up in direct comparison. One of the key trials involved hill climbing performance. When the test began, the Sherman ascended the slope steadily and without hesitation. Its synchronized manual transmission allowed smooth gear changes, while the engine delivered consistent power throughout the climb. The driver maneuvered the tank with confidence, showcasing an ease of handling that would later become one of the Sherman's defining traits. The Panther followed. Its formidable 700-horsepower Maybach 230 engine enabled it to keep pace, but only marginally and with noticeably greater effort. The Ferdinand, weighing approximately 65 tons and equipped with an advanced electric transmission system, fared far worse. Partway up the incline, it lost momentum and stalled completely. Recovery crews struggled in full view of dozens of senior officers and industrial executives. The failure was both public and deeply embarrassing. Speer watched the scene unfold, an experience that would leave a lasting impression. Years later, in his memoirs, Speer reflected on similar observations made during his inspection tour of Italy in October 1944. He noted that reports from the field consistently praised the Sherman's cross-country mobility. According to German assessments, the tank was capable of climbing mountainous terrain previously considered impassable for armored vehicles. Speer attributed this performance to the Sherman's favorable power-to-weight ratio, which granted it superior mobility on both level ground and rough terrain. The 26th Panzer Division had specifically highlighted this advantage in its reports. These conclusions, coming from Germany's own Minister of Armaments, carried considerable authority within Wehrmacht circles. A carefully worded public acknowledgement appeared in the newspaper Das Reich on June 27, 1943. The article described the Sherman as a notable achievement of North American research and praised it as an impressive product of the American steel industry. It emphasized the efficiency of serial production and the tank's alignment with the demanding standards of the North American automotive sector. The article also referenced the Sherman's gyro-stabilized gun, recognizing it as the first practical implementation of such a system anywhere in the world, an implicit admission of American innovation. Though the language was crafted to avoid any hint of defeatism, it masked a growing unease within German engineering circles. Behind closed doors, it was becoming clear that American tanks were not merely sufficient for the battlefield. They were designed from the ground up to endure long campaigns, harsh environments, and continuous use. An approach that fundamentally reshaped what armored warfare could demand from a machine. During the summer of 1943, testing at the German proving grounds near Kummersdorf entered a new phase. What had begun as routine evaluation turned into months of intensive trials that stretched well into the autumn. German engineers subjected captured M4 Sherman tanks to sustained operational testing, deliberately pushing them beyond normal usage limits to observe long-term mechanical behavior rather than short bursts of peak performance. One of the first surprises came from endurance trials. Shermans were driven continuously over long distances, often without major servicing. The results were unsettling for the evaluators. Several vehicles accumulated more than 2,000 kilometers of operation before requiring serious mechanical attention. In practical terms, this was roughly 4 times the effective field range German engineers had been able to achieve with early production Panther tanks, which often failed long before reaching such distances under combat conditions. Transmission analysis deepened the concern. Measurements revealed that the Sherman's drivetrain lost significantly less power between the engine and the tracks than any contemporary German tank. Efficiency levels exceeded those of German designs by a clear margin. The engineers paid particular attention to the Sherman's synchronized manual transmission, which allowed smooth gear changes without complex techniques. Unlike German gearboxes, it did not demand double clutching or precise engine speed matching skills that required extensive driver training and constant concentration under stress. Even more troubling were findings related to the final drive assemblies. German Panthers relied on a final drive concept inherited from the Tiger tank, a design that looked robust on paper but proved fragile in real-world use. Straight-cut gears housed in relatively light casings struggled to handle the mechanical loads imposed by a vehicle weighing over 45 tons. Reports from both North Africa and the Eastern Front had already described frequent final drive failures, sometimes after movements of less than 100 kilometers, forcing crews to abandon otherwise intact tanks. The Sherman followed a radically different philosophy. Its final drives employed herringbone gear geometry, similar to its transmission, distributing loads more evenly and reducing stress concentrations. Failures were rare, even during prolonged combat operations that routinely destroyed German components. Decades later, restoration teams would discover Sherman final drives still functional after years of storage, requiring little more than cleaning. Clear evidence that the design had been built with generous safety margins far beyond immediate battlefield demands. By late 1943, Kummersdorf engineers had gathered enough empirical data to compile extensive internal reports. These documents circulated quietly through Wehrmacht technical offices and the Armaments Ministry, intended for senior officers rather than public consumption. Their conclusions were sobering. The Sherman, the reports noted, was not an elegant machine in the traditional German engineering sense. Its construction lacked the meticulous tight tolerances prized by German industry, yet this apparent imprecision turned out to be a strength. American manufacturing methods produced vehicles that were more tolerant of dirt, wear, and misuse, performing reliably under harsh conditions where German tanks often failed. Interchangeability of parts emerged as a decisive advantage. Field repairs on Shermans could be carried out with basic tools and limited training. Crews and mechanics did not require factory-level precision or specialized equipment. German vehicles, by contrast, often demanded exact alignment and expert intervention, making frontline repairs slow, difficult, or impossible. The reports emphasized that this difference was not merely technical but industrial and cultural. American automotive engineering reflected decades of civilian mass production experience. Before the war, automobiles in the United States were everyday tools used by millions across social classes. Germany, by comparison, had never developed civilian car ownership at a similar scale. Vehicles remained luxury items for elites, and the much-publicized Volkswagen program, launched in 1934, had delivered fewer than 1,000 civilian cars by the outbreak of war. This imbalance shaped tank design at a fundamental level. American tanks were engineered so that mechanics with ordinary civilian automotive backgrounds could maintain them using familiar principles. German tanks assumed the presence of highly trained specialists with years of dedicated military technical education, an assumption that proved unrealistic as the war expanded. As battlefield reports accumulated through late 1943 and early 1944, the reliability gap became impossible to dismiss. Panther units were forced to operate under strict mechanical limitations. Drivers were warned to avoid frequent gear changes, as excessive shifting damaged transmissions. Third gear was particularly fragile and officially discouraged except in emergencies. Panthers were forbidden from turning while reversing, as this could destroy the drivetrain entirely. Pivot turns were only permitted when resistance was perfectly balanced between both tracks, severely restricting maneuverability. Even minor environmental factors posed risks. Debris caught in the running gear could jam drive sprockets, immobilizing the tank for hours while crews attempted repairs under combat conditions. These vulnerabilities existed despite Panthers being produced in specialized tank factories by skilled workers using Germany's best available materials. The Sherman told a different story. Designed by engineers from General Motors, Ford, and Chrysler, it embodied principles refined through decades of civilian vehicle production. Its creators prioritized durability, ease of maintenance, and operational continuity over theoretical performance figures. The result was a machine that may not have impressed on paper, but one that kept moving, fighting, and returning to service when others could not. The American M4 Sherman was conceived with a design philosophy deeply rooted in the practices of the civilian automotive world. Wherever feasible, its engineers deliberately relied on commercially proven vehicle components, drawing directly from established industrial supply networks and mass production know-how. This approach allowed the tank to benefit from decades of automotive experience rather than relying solely on bespoke military engineering. A striking example of this philosophy was the Sherman's transmission system. Instead of being produced by a single specialized firm, identical transmissions were manufactured simultaneously by several major American companies, including Caterpillar Tractor, Buick, and the Ford Motor Company. All units were built to the same technical standards, meaning parts from different factories could be swapped freely without recalibration, fitting, or adjustment. This level of true interchangeability was second nature in American industry, but it stood in sharp contrast to German tank production, where even vehicles of the same model often contained subtle factory-specific differences that made component replacement complicated or impossible in the field. Captured Sherman tanks began arriving at the German Testing and Evaluation Center at Kummersdorf as early as 1943, with additional vehicles following throughout 1944. These included tanks seized from British formations in Italy as well as Shermans taken intact from Soviet units on the Eastern Front. Each vehicle was subjected to a standardized testing regime designed to assess performance, durability, and mechanical behavior. Over time, this process produced an extensive body of data covering multiple Sherman variants and different production batches, offering German engineers an unusually complete picture of American armored design. Particular attention was paid to British modified Shermans fitted with the powerful 17-pounder anti-tank gun. Known as the Firefly, this variant was developed to overcome the Sherman's well-known shortcomings in firepower. German engineers studied these vehicles closely and were struck by how easily the larger gun had been accommodated. The Sherman's wide turret ring allowed the weapon to be installed with relatively minor structural changes, revealing a level of foresight and growth margin embedded in the original design. This adaptability stood in stark contrast to German armored vehicles of the same era. The Panther, which had been rushed into service to counter the Soviet T-34, possessed no such flexibility. Its turret and internal layout left virtually no room for significant weapon upgrades. Any attempt to mount a substantially more powerful gun would have required a complete redesign of both turret and hull, a limitation that became increasingly problematic as the war progressed. Beyond structural analysis, the Kummersdorf program expanded into extensive reliability testing intended to mirror battlefield conditions as closely as possible. Shermans were driven for hundreds of kilometers across rough terrain, with engineers meticulously documenting every malfunction, repair interval, maintenance task, and component failure. These controlled trials were then compared against operational reports submitted by Panther and Tiger units fighting in both Eastern Europe and Italy. The results were impossible to ignore. Throughout most of 1943, Panther units reported average operational readiness rates below 40%. In some formations, the situation was far worse, with only 20 to 25% of vehicles serviceable at any given time. Entire battalions recorded periods when fewer than 1 out of every 5 Panthers was capable of entering combat. Shermans, by contrast, consistently demonstrated far higher availability across all theaters of war. German field records provided grimly detailed accounts of Panther reliability problems. During Operation Citadel at Kursk in July 1943, mechanical failures rendered more Panthers inoperable than enemy fire, leaving only 16% fit for combat. By December of that year, readiness had improved but still reached only 37%. Subsequent reports showed slow progress. February 1944 again recorded 37% operational status. By April, this climbed to 50%, and in May 1944, Panthers finally achieved a peak readiness rate of 78%. Even this figure represented the proportion of tanks merely capable of action on a given day, with the remainder sidelined for repairs or awaiting spare parts. Despite steady improvements, Panther availability never equaled the reliability Shermans displayed from their earliest production runs. By late 1943, the broader pattern had become clear to any engineer or analyst willing to examine the data objectively. Sherman diesel engines routinely exceeded 3,000 kilometers of service life when properly maintained. Panther engines, even after corrective modifications, struggled to reach 1,000 kilometers. German technical reports from March 1944 described engine lifespans of 700 to 1,000 kilometers as a significant achievement, a claim that only underscored how far behind they remained. At best, Panther engines achieved roughly one-third of the service life expected from their American counterparts. Transmission performance told a similar story. Sherman gearboxes were robust, required infrequent overhaul, and featured synchronized gears that reduced the likelihood of driver-induced damage. Panther transmissions, on the other hand, were fragile and maintenance-intensive. Failures of third gear were so common that crews routinely skipped it altogether, shifting directly from second to fourth to avoid breakdowns. Final drive systems further highlighted the gap. Sherman final drives functioned reliably under conditions that routinely destroyed Panther final drives after as little as 100 to 200 kilometers of use. Operational experience reinforced these findings. German units that managed to capture Shermans in usable condition eagerly put them into service, particularly as their own armored formations suffered mounting mechanical attrition. Unlike captured Soviet T-34 seconds, which often required extensive modification before use, Shermans entered German service essentially unchanged. They required no fundamental redesign because, quite simply, they functioned as intended. Crew reactions were telling. Tankers accustomed to frequent breakdowns in Panthers and Tigers repeatedly expressed astonishment at the Sherman's dependability. Letters and after-action reports describe a vehicle that inspired confidence rather than anxiety. German regimental reports noted that Sherman crews could concentrate on tactics, coordination, and combat effectiveness, while Panther and Tiger crews were perpetually concerned about whether their vehicles would survive the journey to the battlefield or complete a mission before mechanical failure brought operations to an abrupt halt. One of the final documented examples occurred in January 1945 during Operation Nordwind, when the 10th SS Panzer Division captured 12 M4A3 Shermans near Hellesheim. Even at this late stage of the war, German forces recognized the practical value of a tank whose greatest weapon was not its gun or armor, but its ability to function reliably when it was needed most. The armored vehicles in question had originally served with the U.S. Army's 43rd Tank Battalion. During a sudden and forceful German offensive, their American crews were compelled to abandon them, leaving the machines largely undamaged. Rather than being scrapped or studied only in isolation, 12 of these captured Sherman tanks were pressed directly into German service. They were reorganized as a newly designated 13th Company within the 10th SS Panzer Regiment and remained operational for the rest of the conflict. Within German formations, these Shermans were not used as frontline breakthrough tanks. Instead, they were assigned roles that placed heavy demands on mechanical endurance, reconnaissance missions, and mobile reserve duties. These tasks required vehicles capable of traveling long distances continuously, often under combat pressure, without the luxury of frequent maintenance halts. In this environment, mechanical dependability was not a secondary feature, it was the defining factor. German field commanders quickly reached a conclusion that echoed findings made years earlier during technical evaluations at the Kummersdorf proving grounds. American tanks, whatever their shortcomings in armor thickness or gun caliber, could be trusted to operate when called upon. By the final stages of the war, this reliability outweighed all other tactical considerations. A Sherman that arrived on the battlefield with a functioning engine and a working main gun was, in practical terms, far more valuable than a Panther boasting superior firepower but immobilized dozens of kilometers behind the front due to mechanical failure. As the strategic situation deteriorated for Germany, testing programs expanded. In January 1944, with Wehrmacht forces retreating on multiple fronts, increasing quantities of captured Allied equipment were transported back to Kummersdorf for systematic examination. German engineers undertook a detailed study of several Sherman variants, focusing in particular on their propulsion systems and overall automotive design. The M4 model, equipped with the Continental RA 975 radial gasoline engine, was carefully documented, with its performance characteristics compared against other Sherman configurations. Engineers also evaluated the M4A2 variant, which used a pair of General Motors 6046 diesel engines. This version immediately drew attention for its fuel efficiency and distinctive operating behavior. The M4A3, powered by the Ford GAA Vake gasoline engine, widely regarded by American crews as the finest Sherman power plant, was also subjected to close scrutiny. Despite differences in engines, fuels, and layouts, all variants shared a common and unmistakable trait. Each demonstrated exceptional mechanical reliability. This consistency was not accidental. It reflected conservative but effective engineering choices, rigorous standardization, and high manufacturing quality across multiple factories. For German engineers, this uniformity was striking. They were accustomed to seeing notable performance differences between vehicles that were, on paper, identical but produced by different manufacturers under wartime pressure. Among all the examined models, the diesel-powered M4A2 left the strongest impression. Thousands of these tanks, over 4,000 units, had been delivered to the Soviet Union under the Lend-Lease program, and many were subsequently captured by German forces during retreats on the Eastern Front. The twin GM 6046 diesel engines delivered performance comparable to any gasoline-powered Sherman while consuming significantly less fuel. At a time when German fuel reserves were shrinking rapidly, this efficiency represented a major operational advantage. German designers had explored diesel engines for armored vehicles earlier in the war but ultimately abandoned the concept. Complex fuel injection systems and production challenges were deemed incompatible with German industrial realities. In contrast, American industry managed to produce diesel and gasoline Sherman variants simultaneously without disrupting output or schedules. This ability highlighted a level of industrial flexibility and technical maturity that German wartime production never fully achieved. By March 1944, official German assessments began to reflect modest progress in their own armored vehicle reliability. General Heinz Guderian, serving as Inspector General of Panzer Troops, reported through formal channels that improvements to the Panther tank had finally brought it to what he described as an acceptable operational standard. Engine lifespan had increased to between 700 and 1,000 kilometers, and chronic final drive failures had been mitigated through redesigns and tighter manufacturing controls. Within German military communications, these developments were celebrated as major achievements. Yet, in a broader context, they merely represented parity with reliability levels that American Sherman tanks had demonstrated since their introduction in 1942. The contrast was stark. German armored forces were applauding progress that only allowed them to reach standards the Allies had met from the outset. This disparity became even more pronounced as Germany's industrial base came under escalating strain. Shortages of raw materials intensified, while Allied strategic bombing campaigns increasingly targeted critical nodes in the German armament supply chain. Panther and Tiger production suffered in particular as key facilities were singled out with growing precision. One of the most devastating blows occurred on the night of April 27-28, 1944, when Royal Air Force Bomber Command launched a massive raid against Friedrichshafen. A force of 322 aircraft struck the Maybach Engine Works, the primary producer of engines for Germany's heavy tanks. According to records held by the Imperial War Museum, the attack stands as the single most destructive bombing raid against German tank production during the entire war. The adjacent ZF gearbox factory was also destroyed. The consequences were immediate and severe. Production of tank engines and transmissions ceased entirely for approximately 6 months. When manufacturing finally resumed in November 1944, the damage went beyond physical infrastructure. Skilled labor had been lost, supply chains disrupted, and quality control standards sharply degraded. The result was armored vehicles that, even on the factory floor, no longer matched earlier benchmarks, further widening the gap between German ambitions and battlefield realities. As the Second World War dragged on, Germany's armored vehicle industry found itself under growing strain. With large numbers of skilled German workers drafted into the armed forces, factories increasingly relied on forced labor drawn from occupied territories and concentration camps. This workforce, operating under brutal conditions and with no loyalty to the regime, often engaged in subtle but deliberate acts of sabotage. Foreign objects were pushed into lubrication channels, seals were fitted incorrectly, and mechanical assemblies were completed without respecting essential tolerances. Individually, these flaws were hard to detect. Collectively, they were disastrous. Nothing comparable occurred in American tank production, U.S. Factories were located far from enemy bombers, staffed by civilian workers earning solid wages, protected by labor laws, and motivated by both patriotism and material incentives. As a result, quality control remained consistent throughout the war. The contrast between German and American tank production was therefore not rooted in intelligence or technical knowledge, but in industrial organization, manufacturing philosophy, and the human conditions behind the assembly lines. German engineers were not inferior in theory. On the contrary, they possessed deep academic training, strong scientific backgrounds, and a thorough understanding of mechanical and automotive principles. The problem lay in how those principles were applied. German tank design repeatedly favored extreme battlefield performance, thicker armor, larger guns, higher theoretical lethality while neglecting durability, ease of maintenance, and long-term mechanical reliability. The Panther tank exemplified this imbalance. Its high-velocity 75mm K-42 cannon and heavily armored front made it formidable on paper and deadly in ideal combat situations. Yet these advantages were paid for with an overstressed drivetrain that struggled to carry a vehicle weighing approximately 45 tons. The final drive system in particular proved fragile, failing under sustained use. The Tiger tank followed a similar pattern. While terrifying to face, it demanded constant attention, specialized tools, and mechanics with advanced training simply to remain operational. Such compromises might have been acceptable if Germany had possessed the industrial depth to produce large numbers of tanks along with ample spare parts. It did not. As Allied bombing intensified and shortages of fuel, steel, and skilled labor worsened, German industry was pushed beyond its limits. Replacement parts became scarce, repairs were delayed, and frontline units were left with vehicles that could not be kept running. Across the Atlantic, American tank designers approached the problem from a radically different angle. Drawing on decades of experience in civilian automobile and truck manufacturing, U.S. engineers prioritized standardization, mechanical simplicity, and reliability. Tanks were designed to be built in enormous quantities and maintained by mechanics whose skills closely resembled those used in civilian garages. Proven commercial components were adapted for military use rather than inventing complex systems from scratch. The Sherman tank embodied this philosophy. Its powertrain relied on engines and transmission concepts already validated in civilian service. Even features that seemed unimportant on paper proved critical in combat. For example, the Sherman's electrical system included an auxiliary generator that allowed the turret to rotate even when the main engine was not running. German designers saw no need for such a feature, considering it an unnecessary complication. In practice, it saved lives, especially when Shermans were forced to halt on inclines or rough terrain, situations where German tanks often lost turret control if the engine stalled. German crews were painfully aware of these shortcomings. Accounts from tankers describe moments when enemy vehicles retained full combat capability while German turrets froze in place due to minor mechanical failures. These practical details never appeared in German design specifications because they were overshadowed by the obsession with armor thickness and gun caliber. By early 1944, reports from Wehrmacht units across all theaters painted a bleak picture. Manufacturing standards were slipping, breakdowns were rising, and spare parts were increasingly unobtainable. Panthers, in particular, could not be trusted for long-distance movement. Any march exceeding roughly 100 kilometers required rail transport, as their final drives frequently failed under continuous road use. Commanders issued strict orders limiting vehicle movement, preferring to preserve tanks for battle rather than lose them before reaching the front. Even recovery vehicles were affected. The Berger Panther, designed to tow disabled Panthers, was built on the same chassis and inherited the same mechanical weaknesses. In many cases, recovery efforts resulted in yet another immobilized vehicle. The consequences were severe. Some German units reported that the majority of their tank losses, up to 70%, were caused not by enemy fire but by mechanical failure. Tanks were abandoned, destroyed by their crews, or simply left behind due to lack of spare parts or repair capacity. Meanwhile, American production surged forward at a scale Germany could never hope to match. Over the course of the war, U.S. factories produced 49,324 Sherman tanks, exceeding the total number of all German tanks of every type combined. Thousands were delivered to British and Commonwealth forces through the Lend-Lease program. The Soviet Union received more than 4,000 diesel-powered Shermans, while Chinese units fighting in Burma used them effectively against Japanese armor that was inferior to both American and German designs. Every battlefield echoed the same conclusion previously demonstrated in controlled testing at Kummersdorf. When properly maintained, Shermans continued operating under conditions that crippled German vehicles. This reputation was not lost on the enemy. German crews who captured Shermans frequently chose to use them, praising their mechanical reliability in letters, official reports, and post-war interviews. Perhaps most telling were comments from German mechanics on the Eastern Front. Even the notoriously complex Chrysler A57 multibank engine, comprised of 5 separate engine blocks, was often described as easier to diagnose and repair than German tank engines that demanded specialized tools and rare expertise. In the end, the story of Sherman versus Panther or Tiger was not a simple contest of firepower or armor. It was a clash between two industrial philosophies, one that chased perfection on the drawing board and another that valued practicality, consistency, and the realities of mass warfare. History ultimately revealed which approach proved more sustainable. The Ford GAA Vate engine, widely recognized by Allied tank crews for its combination of power and dependability, consistently impressed German technicians who were accustomed to Maybach engines. Unlike the Maybach designs, which demanded frequent adjustments of valve clearances, ignition timing, and carburetor settings, the Ford power plant demonstrated remarkable stability under operational conditions. Similarly, the General Motors twin diesel engine, initially considered inferior to gasoline engines by the U.S. Army and assigned largely to Lend-Lease production, outperformed any diesel tank engine that Germany had produced, both in reliability and operational output. The Sherman tank's broad design tolerances provided an additional advantage that German engineers quickly noticed. The original transmission and final drive systems, engineered for a 30-ton M4 equipped with a 400-horsepower engine, required virtually no modification to accommodate the heavier 42-ton M4 R3E2 Jumbo with its substantially thicker armor. These same components successfully transmitted up to 650 horsepower from experimental engines without any mechanical failures or reinforcement. German engineers often regarded such over-engineering as wasteful, a needless expenditure of resources and materials with little immediate benefit. In contrast, American designers saw these generous margins as an investment in the tank's long-term performance, allowing for future upgrades and ensuring consistent battlefield reliability. By the summer of 1944, as Allied forces launched their invasion of Normandy, German tank commanders were fully aware that their technological disadvantages extended beyond the capabilities of individual tanks. American forces combined superior artillery, overwhelming logistical support, and devastating close air support to achieve battlefield dominance, regardless of the specific tank models in play. The exceptional reliability of the Sherman meant that American armored units could maintain a high operational tempo, launching attacks, sustaining engagements, pursuing retreating forces, and rapidly redeploying without lengthy maintenance interruptions. German panzer divisions, by contrast, were forced to conserve their limited operational vehicles, aware that every maneuver consumed critical component life and increased the risk of breakdown. Operational availability thus became a decisive factor, determining which side could sustain offensive pressure and which had to ration combat resources carefully. The use of captured Shermans by German units offered further evidence of the Americans' mechanical advantage. During the Battle of the Bulge in December 1944, the 150th Panzer Brigade, organized for infiltration missions, sought to acquire American tanks to disguise its movements. Shermans were specifically requested due to their reputation for dependability. However, only 2 tanks were captured, and of these, just one was fully serviceable, yet it never saw combat because logistical obstacles and traffic congestion prevented the mission from proceeding. Operations requiring vehicles to perform reliably far behind enemy lines highlighted the superiority of American engineering. German tanks, even when operational, could not sustain the continuous performance such missions demanded. The stark reality of German mechanical limitations was formally acknowledged on January 23, 1945. At a Panzer Commission meeting, a report detailed widespread failures in final drives across German tank models. The findings revealed severe deficiencies: 500 defective final drives in Panzer IVs, 370 in Panthers, and around 100 in Tigers, with roughly 200 additional failures in Hetzers based on the Czech 38-ton chassis. General Wolfgang Thoma, serving as Chief of Staff under Inspector General Guderian, emphasized the operational consequences in unambiguous terms. Orderly deployment of tanks was rendered impossible. Crew confidence in their vehicles eroded, and in some cases, entire tanks were abandoned to avoid being stranded by mechanical failures. Despite their imposing specifications and battlefield reputation, German tanks failed in their fundamental purpose: mechanical reliability sufficient to reach the battlefield and complete assigned missions. By early 1945, the Kummersdorf testing facility was preparing for evacuation as Soviet forces advanced inexorably on Berlin. A grim acknowledgement of Germany's inability to produce armored vehicles capable of sustaining the demands of modern mechanized warfare. As the war neared its conclusion, German engineers scrambled to safeguard critical technical data. Testing records and documentation were hurriedly transported to facilities further west, an attempt to ensure that the technological insights they had developed could be examined and utilized after the conflict ended. Among the captured Allied vehicles, a small number of Sherman tanks, at least 2, were temporarily pressed into service by German forces during the chaotic defense of Berlin. These tanks operated alongside standard German armor, participating in the final, desperate engagements and offering a rare opportunity to compare foreign and domestic designs under actual battlefield conditions. The Shermans remained operational until they were either destroyed by combat or abandoned due to depleted fuel reserves. In contrast, German tanks, including Panthers and the few surviving Tigers, suffered frequent mechanical failures, often in situations that experienced crews, accustomed to the already fragile reliability of German machinery, found alarming. The story of War Daddy II and the other Shermans tested at Kummersdorf underscores the stark contrast in industrial approaches between the United States and Germany during the Second World War. German tank engineers, operating within a system that emphasized theoretical perfection above practical functionality, created machines that appeared impressive on paper but were prone to breakdowns during prolonged field operations. By contrast, American designers leveraged decades of automotive engineering expertise, producing tanks that, while lacking in technical sophistication in certain aspects, delivered dependable performance under the harsh conditions of active combat. In armored engagements, as in warfare more generally, the vehicle that can perform consistently under pressure holds a decisive advantage over one that might theoretically be superior but fails to endure the realities of the battlefield. Post-war investigations by American and British intelligence corroborated what German testing at Kummersdorf had already indicated: mechanical breakdowns accounted for as many losses as direct combat damage. Final drives fractured under stress, transmissions seized due to poor lubrication or operator mistakes, and engines failed from overheating or oil starvation. The German focus on individual vehicle excellence and headline-grabbing specifications overlooked a fundamental requirement: reliability and ease of maintenance. German tanks demanded intensive expertise for operation and repair. They required highly trained technicians to maintain engines that were sensitive to mismanagement, supported by a supply chain unable to cope with the complexity of unique components spread across scattered units. These challenges revealed that advanced design alone was insufficient if vehicles could not be kept running under combat conditions. The lessons drawn from Kummersdorf testing directly influenced post-war German tank development. In the 1952, the Federal Republic of Germany, embarking on the design of the Leopard 1 main battle tank, deliberately prioritized reliability and maintainability over raw technical performance. Drawing inspiration from American automotive engineering, German designers incorporated practical engineering principles into military vehicle development. The Leopard 1 featured a robust powertrain with generous tolerances, simple maintenance procedures requiring minimal specialized tools, standardized parts to allow rapid field repairs, and a modular design that enabled upgrades without complete overhauls. The Leopard 1 emerged as one of the Cold War's most successful tank designs, adopted by numerous armies and produced over several decades. The captured Shermans at Kummersdorf, including War Daddy II with its identifying markings still visible, served as more than just captured enemy hardware for study. They provided concrete evidence that industrial experience and pragmatic engineering could outweigh sophisticated but impractical innovations. German designers' pursuit of high specifications stemmed from the belief that superior technology could offset resource shortages and numerical inferiority, yet the Shermans demonstrated that durability, maintainability, and reliability were decisive factors in combat effectiveness. American tank engineers approached armored warfare with a philosophy grounded in practical experience rather than abstract technical specifications. Through repeated trials and the harsh lessons of combat, they learned that the decisive factors in mechanized warfare were not peak performance on paper, but the ability to keep vehicles operational, maintainable, and ready for prolonged campaigns. Their insight proved accurate, and it ultimately shaped the outcome of the war. The contrast between the dependable Sherman tanks and the technically advanced yet fragile German vehicles influenced not only battlefield tactics, but also the broader understanding of how industrial capacity and production strategy underpin military effectiveness. At the outbreak of World War II, Germany held a clear advantage in certain technological domains. Its weapons systems often outclassed those of other nations, reflecting a deep reservoir of scientific knowledge and engineering skill. Yet this technical edge came with a severe limitation. The German industrial base was unable to sustain mass production at the scale necessary to fully leverage these advantages while simultaneously conducting a multi-front war. In contrast, the United States entered the conflict with weaponry that, in many respects, was less sophisticated than that of Germany. However, the US possessed a manufacturing infrastructure capable of producing vast quantities of reliable equipment, continuously refining both design and quality in response to combat feedback. The Sherman tank exemplified this approach. Though it was not the most heavily armed or armored tank of the war, its reliability and ease of maintenance allowed American forces to field and sustain armored units far more effectively than their German counterparts. Whereas German tanks often broke down or required extensive repairs before or during operations, Shermans could be counted on to reach the battlefield and remain functional. Operational readiness in this context was a far more critical metric than raw firepower. A battalion with the vast majority of its vehicles mission-capable could undertake operations that a similarly sized German unit, plagued by mechanical failures, simply could not attempt. By mid-1943, extensive testing at German facilities, such as the Kummersdorf Proving Grounds, confirmed this reality. German engineers rigorously examined captured Shermans, documenting their performance in exhaustive reports. These analyses repeatedly demonstrated that the mechanical reliability of American tanks far exceeded that of German designs, even when the latter featured technically superior guns or armor. The findings were unambiguous. While German engineers correctly identified the advantages of American industrial practice, their nation lacked the manufacturing flexibility and scale to implement similar reliability-focused production methods while engaged in a losing war on multiple fronts. The United States, by contrast, had decades of experience in commercial automotive manufacturing, where reliability, maintainability, and operational consistency were critical to market success. These principles were seamlessly extended to military production, enabling the US SOC to create not only tens of thousands of Sherman tanks, but also vast quantities of virtually every other type of weapon. Combined with the Lend-Lease program, which supplied allies with essential equipment and a civilian economy that maintained high standards of living, American industrial performance created a force multiplier that Germany could not match. The numerical and practical advantage was stark. The US produced nearly as many Shermans as Germany produced all types of tanks combined, and each Sherman could be deployed with confidence that it would function reliably under combat conditions. In contrast, even the most impressive German tanks, such as the Panther and Tiger, often proved unreliable, undermining tactical plans and eroding operational capability. The simple mathematics of war were clear. A less powerful tank that consistently reached the front and fought effectively was exponentially more valuable than a technically superior vehicle that frequently failed or required days of maintenance for each day of combat. The case of the Sherman tank captured in Tunisia, tested exhaustively at Kummersdorf, illustrates this perfectly. Every mile it traversed without mechanical failure, every successful mission it completed, provided concrete evidence of the effectiveness of American industrial practice. These results were a sobering lesson for German engineers and military planners. Reliability and production capacity were decisive factors that no amount of technical brilliance alone could overcome. German reports acknowledged the reality, yet the industrial and strategic limitations of Germany made it impossible to fully address the problem. Ultimately, the Sherman's success lay not in its specifications, but in the US approach to industrialized warfare. Its widespread availability, ease of maintenance, and mechanical dependability allowed Allied forces to operate armored units at a scale and intensity that Germany could not match. German engineers had correctly diagnosed the advantage but lacked the capacity to act on it. The war, therefore, was decided as much by factories, production lines, and industrial foresight as by battles on the front lines. The Sherman tank, unremarkable in design but extraordinary in its operational reliability, symbolized the triumph of industrial competence over technical sophistication, providing decisive evidence that the US had already won the production war even while fighting continued on multiple fronts.